So let's start off by talking about what OpenMP is. Well, OpenMP stands for Open Multiprocessing. At one time, multi-threading an application was an option. It was something that was nice, but not essential. Now, in today's market, with the demand for high-performing applications, multi-threading is essential. So normally OpenMP is used in C, C++, and Fortran. When I've done iOS and Android programming, I have searched high and low for an equivalency, and there have been attempts made, but nothing comes close to the OpenMP standard that C, C++, and Fortran enjoy. It is multi-platform, so you can go from a Windows box to a Linux box to a Solaris box and enjoy the same OpenMP standards that you do on the other platforms. So I'm going to use Visual Studio, and so the current version for this demo is going to be Visual Studio 2013. The first thing I did in order to enable OpenMP was to include Openmp.h, and the next thing I did was to set the project properties. So let me go ahead and show you that now. Okay, so here I am in Visual Studio. I haven't written any kind of code, but I have included Openmp.h, and I have made sure that the OpenMP support is turned on. So that's the extent of the setup you need to do in Visual Studio. In order to show you OpenMP and how it can affect performance, we first need a demo program that will show you the baseline performance without OpenMP. This demo program relies on math functions such as square root, cosine, sine, and tangent in order to really provide a CPU-intensive experience. Okay, just a bit of housekeeping. I included Windows.h and Math.h because I needed some functions in those header files. The next thing I did was I created a huge data array, and we're going to use that data array and perform operations to it. Here I recorded the start time in milliseconds, and I went through a loop, calculating a square root, cosine, sine, and tangent. Finally, I got the elapsed time and printed it out. Okay. So let's go ahead and see what we have here and see what happens. Okay, 3354 milliseconds, just over 3 seconds. And please note that this program is already compiled in release mode. Okay, so in order to parallelize a loop using OpenMP, it just simply requires a single pragma statement. So let's break it down. Starts off with pound pragma, which this just tells the compiler we're going to give it some extra information. The next thing is OMP, and what this is doing is asking for OpenMP support. The next statement is parallel. This tells OpenMP we want to employ a parallel structure. And finally, the word for means we're going to apply this to a for loop. So pound pragma, OMP, parallel for. It's that simple. So let's take a look at the performance improvements once the rubber hits the road, once we add the OMP pragma statement. Pragma, OMP, parallel, for. And it should be a simple matter to build this. Now we'll run it and see what kind of performance gain we got. So now instead of 33 something, or just over 3 seconds, we have 1,389 milliseconds. So basically we cut the execution time into a third. Let's talk now at a high level about how OpenMP does its work. For this discussion, let's say OpenMP splits into 3 different threads. Now, how many threads OpenMP splits into is up to OpenMP at runtime. It will determine the optimal number of threads for that situation. So the first thread will perform operations on indices 0, 3, 6, 9, and so forth. In other words, every third array element it's going to act on. The second thread will perform operations on indices 1, 4, 7, 10, and so forth. still every third array element, but it will start at a different array index, 1 in this case. The third thread will perform operations on indices 2, 5, 8, 11, and so forth, still every third array element, but we're starting at array index 2, so it gets all the other array indices that threads 1 and 2 missed. So here's a picture that I created. The main thread splits into 3 threads, and each thread is color-coded, showing which array element it is affecting. And then there are color-coded lines pointing to the array elements. It's a little confusing since they're overlapping, but you can still get the general idea. There is something you need to consider when using OpenMP, and that's data races. And you can use reducers to mitigate that. What a data race is when multiple threads are trying to access a single memory location. Now, this is bad because let's say 2 threads are trying to add different values into the same memory location. Well, you never know what's going to happen depending on the exact split second that they're accessing it. So this is going to give you unpredictable results. It's called a data race. The example we use doesn't have any data races because each thread is on different array elements. But OpenMP offers a reduction clause to mitigate this. So the following code example protects against data races on a variable named value for all addition operations. And as you can see, it says pound pragma, OMP, parallel for, and then comes the reduction clause, specifying addition with a plus, and the name of the variable, value. So my conclusion is that OpenMP is awesome. I use it all the time. With it, you can easily parallelize many loops and provide amazing performance improvements for your applications.